Welcome back. Now we talk about why we actually need slope-intercept form. So you might have been wondering that because sometimes it seems like, well, why can't we just put all the variables on one side and just graph it that way, where we can do intercept method all the time and don't even worry about slope? Well, we're going to talk about this. We have to worry about slope. A lot of times we need slope. We're going to need to define parallel and perpendicular lines. We need to describe lines very well so that we can do algebra with them. And intercept method, although it is wonderful for graphing lines, doesn't give that to us. Even if we can graph the lines, sometimes we won't be able to find slope from the actual graph. So we're going to see that. We're going to explore that with 4 examples, just why we need it, why it even matters. So let's look at the very first one. Could you graph that with intercept method? Yeah, of course. You got all your variables on one side. You got a non-zero constant here. It looks really good. But check out what happens. If you start doing intercept method and you start getting negative 3x equals 8, you get a fairly nasty x-intercept right off the bat. That's negative 8/3, comma 0. Okay, awesome, I guess. The y would be pretty easy, it's 2. But you tell me, how can you find the slope from that? I mean, if you go negative 8/3 and 2, you're going to climb 2, but you're going to go over negative 8/3. You're going to start having some complex fractions when you start trying to find your slope. Do we have to find slope all the time? Not all the time if you just are asked to graph, but graphing and making parallel, graphing, making perpendicular, using other things that we need math for, you're going to need the slope. So this doesn't give it to us very easily. Can you use it to graph? Yes. Should you always? If you're just asked to graph, there's not a problem with that. But if you have to find the slope, solving for y is pretty much your only option in some of these cases. That's one reason why we need slope-intercept form, is so that we can solve for y and immediately identify the slope. That's one big thing. So let's try that with this. Let's see if it makes our graphing easier. Let's also see if it makes finding slope easier. So how would you solve that for y? Remember, we like to leave y's where they are. Unless they're negative, sometimes then we start adding or subtracting them. In this case, I like the y where it is, but in order to find slope, I've got to solve this equation for y. Let's leave that there, get rid of everything around it. Remember with whole terms, when we get rid of whole terms, we're either adding or subtracting. We want zeros for terms because that means they'll be added or subtracted onto our other terms and give us back the things that we want to stay. So add or subtract to get rid of entire terms. That leaves us with positive 4y. Side note, this is going to cause you a lot of grief if you don't catch this, okay? If that had been a minus, you would now have a negative 4y right there. And if you were to divide to solve for y, you'd be dividing by negative 4. I hope you caught that. If that's a minus, that's a negative, and you're divided by negative. It will change every sign. So if you find yourself getting lines that look like this when they should look like this, that means your y-intercept is wrong. That means that you're dividing by a positive when you should be divided by a negative. It'll change where your y-intercept is. That's an issue. Be careful. So now we're left with positive 4y. I always want to make sure slope-intercept is in order. I want my x's first. I want my constants second. Positive 8 gives us a plus 8. And lastly, hey, let's solve for y. Let's divide everything by 4. 4 divided by 4 is 1. 1 times y gives us y. And let's change our fraction. Let's make this a slope. 3/4 x and then plus 2. Right now, on your own, if you can, write down what your slope is, write down what your y-intercept is. If you kind of played along with the whole intercept method that we just did, are you noticing that this gave you the same y-intercept? It still gave you 0 too. But now check this out. We have 0, 2, but for graphing with slope-intercept, all we need is one point and a way to find the next one. The slope gives that to you. Look how this explicitly gives you the slope really nice. You don't have to worry about it. You don't have to guess at it. You don't have to do complex fractions. You don't have to do any fractions really. It's given you the fraction here. It says your slope is 3/4. How you get from point to point to point is you go up 3 and right 4. That's what the rise over run tells you. And since we have a point given to us by our y-intercept, we can go up 3 and over 4, and if we graph that line between those 2 points, I mean, you got it. Man, that almost never happens. I actually hit it, but check that out. It still has the same x-intercept. Now, this is kind of crazy, but yeah, I didn't use the x-intercept to graph this. It doesn't matter. There's 2 methods to graph. You can do intercept method. It'll work. I mean, it'll work, but it won't give you the slope. That's one reason why we need slope-intercept form. The second reason in this example is it's much easier to work with a fraction when it's a slope than when it is an intercept. When it's an intercept, you're kind of guessing. You're approximating where that is. When it's slope, you're not. Do you see what I'm talking about? When you have a y-intercept that's like 3/5, you're guessing where that is on the graph. You're not going to be exactly on that. When it's -8/3, you're really guessing because that 8/3 is a repeating decimal that goes forever. You're approximating that. Now we can do it well, but it's not as exact as when we have a solid point on a y-axis and then you use your slope to find the next point. That's 2 reasons why we use this. Number 1, it gives us the slope explicitly. That's a big deal. Number 2, well, sometimes it helps us to avoid those nasty fractions. That's an idea here. So graphing itself, either way, man, either way. But as far as finding slope, we need slope-intercept. I hope that will make sense to you. Kind of nice. This next one. Let's try this, because right now that looks awesome for the intercept method. You go, yeah, totally. I got constants on one, or sorry, variables on one side, constant on the other. We can totally do this. Check this out. So how does intercept method work? That cover up the y. Plug in 0 for the y is what we're doing. -2x equals 0. Divide by -2. 0 divided by any number is still 0. You go, oh yeah. Hey, x-intercept, 0, 0, done. Cover up the x, we get 3y equals 0. That basically plugs in 0 for the x. We divide by 3, y equals 0. You go, hell yeah, awesome. 0, 0. That's nice. I only got to plot 1 point. Oh, crap, I only got 1. Wait a minute. How many points do you need to plot a line, to graph a line? So you plot 0, 0. And you go, oh yeah, this is plotting. You go, I don't have 2 different points. I have the same point twice. Listen very carefully. That will happen every single time you have a 0 as your constant. Every time. That means something. That means that's a pretty major failing of the intercept method. It is great as long as you have a constant that's not 0. That's what I've been saying the whole time, a non-zero constant. Because if you have a constant that's 0, you're dividing 0 by a number. 0 divided by any number is always 0. That means that you're going to get the same exact point twice every single time. You know what that 0 tells you? If you have 2 variables on one side and 0 on the right-hand side, that says you're going through the origin. It's going to go through the origin. Now the problem is, I don't know how it's going through the origin. There's no way, there's an infinite number of lines that I could put through that one point. That's a problem. Listen. If you don't have an actual number that's not 0, non-zero constant, the intercept method will not work at all. That means that we have to have slope-intercept. We've got to have some way to graph it. So let's solve for y. Now, it's not particularly hard to do. All we have to do is get rid of a term, finish it off, solve for y by dividing by 3. Let's change that into a fraction. Now, how about this question? This is a cool one. Why don't we have a constant? Because of that. Because you didn't start with a 1. If you don't have a constant here, you're not going to have a constant there. Interesting, right? Now check this out. This is going to hopefully put these ideas together, make it gel for you. What's your slope? Let's write it down. What's your b? What's the number being added or subtracted back here? There isn't one. I'm getting excited about it. That means your y-intercept for the least surprising result ever is 0. If you don't have a constant, it says you have a 0 as your y-coordinate for your y-intercept. So you plug in 0 for x, you get 0 for y. Yeah, that's literally what that said to you. So we're going to be going through the origin. It said it. We knew it from before. If you have a 0 there, you're going to go through the origin. Now we have a 0, 0. That's kind of neat. Let me walk through that one more time. If you try to do cover-up, you're going to get 0 twice. It's going to give you an x-intercept of 0, 0 and a y-intercept of 0, 0. That's the same point twice. You cannot graph a line with that. So we have to have slope-intercept. If you solve for y, if you don't have a constant here, you're not going to have a constant here. It's going to tell you the same thing. Yes, you're going through the origin. Your b is 0. Your y-intercept is 0, 0. But notice the change. Because in this format, we can find our slope, it says, sure, it doesn't matter if you're going through the origin. I have a way for you to get the next point. That way is use your slope. From the point, from the only point that we're given in both cases, go up 2, or rises 2, go over to the right 3, and now we can actually do it. It wasn't a surprise we were going through the origin. We saw that 3 different ways, actually. But because we now know about slope-intercept form, we can find the next point and actually graph our line. That's the other reason why we need slope-intercept. So 1, it helps us with fractions sometimes. Number 2, it gives us slope every time. I guess it's 3 reasons. Gives us slope every time. Number 4, intercept method doesn't always work. It fails if we have 0 as our constant. That's a problem. Man, the last 2 are nasty, huh? Let's take a moment, just kind of see what's going on. What do you want to do with them? The first thing is, I don't want to do them. Well, we have some choices here. Let's check this out. Let's look at this. Look at what's really going on. All your variables are on one side. You have a non-zero constant on the other side. If we got rid of the fractions, the intercept method would work. However, if you get rid of the fractions, you'd be multiplying, oh, do you remember? I'm hoping you remember it. You'd be multiplying by the LCD. You'd be multiplying by 4 here and here and here. All the fractions die, but you'd have to divide by -3 when you're done. That's going to give you a nasty fraction very similar to that one. Okay, so maybe not the best choice. You could do it though. It would work. Would it give you the slope? Absolutely not. Intercept method never gives you the slope without having to look at the graph. So it would not give it to you. So if I'm asking you for the slope, I'm basically telling you, solve for y. You have to. Now, how we do that here, watch carefully, I don't want to lose you. How we do that. Don't kill the fractions first. This is one of the very few exceptions that we don't kill the fractions first, because you'll end up going around and around with it. What we do is we solve for y, at least the y term, with all the fractions up there. Now that's not hard to do. That's going to be a matter of either adding or subtracting a term. So in this case, we're just going to add 3/4 x. That doesn't do a whole lot. All that does is says, I'm going, come on, Leonard. I'm going to completely get rid of this term. That's going to create a 0. Hopefully you see the 0 by adding it to both sides. This is completely gone. I'm left with a 1/2 y on the right-hand side. I'm going to make sure it's in order, though. Remember, we're talking about slope-intercept. This stuff got to be in order. 3/4 x plus 1/2. Now check it out. This is where you want to get rid of fractions, but not all the fractions. You can't. It's impossible. You see, when we have slopes that look like this, you can't get rid of those fractions without changing the y. We change the y, we fall out of slope-intercept form. So the y by itself is the most important thing here, even though we're going to get fractions. That's okay. Slope is always a fraction anyway. So what that means is solve for y and then get rid of this fraction only. Whatever this number is, just multiply by your denominator here. That's going to clear this fraction. Yes, you do have to multiply all the fractions. So if I multiply by 2 here to clear that fraction, I've also got to do it just like clearing any other fractions on both the other terms. So basically every single term. Now let's be very careful. Fractions are where people just kind of lose it. Your calculators will do this. If you have a fraction button, you do 2 times 1/2. If you're not the best with fractions, or 2 times 3/4, or 1/2 times 2, it will do that math for you. Or we can simplify. 2 divides 2 one time. Just divide 2 by 2, you get 1. 1 times 1y gives us just y. Killed the fraction. Here, simplify the 4 with the 2. So 2 goes into 4 2 times, and 2 goes into 2 1 time. That leaves us with a fraction of 3/2 x. Do you see the 3/2 come out of it? This 2 is not large enough to completely simplify the 4. Basically, we're saying, how many times does 2 go into 4? Well, that answer, that quotient, remains on your denominator. So 2 divides 4 2 times. So we're going backwards here. Lastly, 2 goes into 2 1 time. 1 times 1 gives us 1. Which one's easier to graph? It's not even a question. That's way easier to look at than that is. And all we did was solve for y. Can you find the slope? Can you find the y-intercept? If you can, I want you to do it now. I want you to practice doing this right now on your own. Write down the m, write down the b, write down the y-intercept, and then graph the line. So with the y-intercept of 0, 1, we had that b of 1. We said, okay, slope is 3/2, number in front of x. 1 is our b, so that gives us 0, 1. From there, up 3 over 2. We graph our line in about 5 seconds. Is there any way for us to look at this and tell what this line looks like? Absolutely not. We can't. I don't know the slope is positive, but as soon as I solve for y, I know the slope is positive. I know I'm climbing. I have to hit that y-axis at a value of y equals 1. That's kind of cool. That's how we graph quickly, and that's how we're sure that we're graphing correctly. Is when we put this in y-intercept form, slope-intercept form. You can find the slope and intercept very nicely. Now the last one. Think about this in your head before we get to it. Would the intercept method work at all? No matter what we do, is the intercept method going to work? If you have a 0 over here, all your variables here, and a non-zero constant, there's no way that's going to work. So even if I were to clear the fractions by multiplying everything by 6, even if I were to do that, I still wouldn't be able to use the intercept method, and it wouldn't give us our slope anyway. So slope-intercept is a very powerful thing for us. Let's solve this for y. You do have 2 options. You can choose to subtract 2/3 x from both sides. You could do that. Or you could add 1/6 y. I'm going to subtract 2/3 x right now because it's very common for people to do this. It's really common. So, if I'm going to get rid of a whole term, I'm adding and subtracting. On the left-hand side, that's gone. That's awesome. On the right-hand side, I'm going to get negative 2/3 x. That's great. I know I'm going to get that. The question is, what goes right there? That's the big one. If you're putting 1/6 y, we're making some pretty serious errors. What I want to make sure that we're not doing is that we're not forgetting that sign. If that's a plus, sure, you get a positive. If that's a minus, we're going to get negative 1/6 y. Now, I just told you that we want to not clear fractions before we get the y term by itself, not the y variable, the y term. And that's true, but we're going to have to be kind of careful here. When we multiply by 6, you're going to notice already I associated the negative with the numerator. If we multiply by 6, that's perfectly fine. It looks really good. But what that's doing, it's simplifying this 6. It's simplifying this 3 with the 6. 3 divides 6 2 times. That 6 is on the numerator. The quotient, it's going to remain on the numerator. So we're going to have that 3 divides 6 2 times. That's going to be on the numerator. 2 times -2 is -4. So on the right-hand side, we get 2 times -2. That's -4 with our x. We're just simplifying fractions here. That's all that's happening. On the left-hand side, what mistake do you think people are going to make? What do you think is going to happen here when they multiply by 6? They're probably, if they're going to make a mistake, give me that. Or they're going to give me this and then get confused on what to do next. If you ever have a numerator, whether it's -1 or -17, I don't care what it is, get rid of your denominator first by multiplication and then just divide. So if we're going to divide, we're going to get rid of that -1 by division. We're basically just dividing both sides by -1. Remember, with addition and subtraction, we're trying to get zeros. With multiplication, we're trying to get positive ones. How we get positive 1 here is dividing a negative by a negative. That gives me positive 1y. On the right-hand side, it also gives me positive 4x. Right now, if you haven't done it, I want you to write out the slope, the y-intercept, and graph that. I obviously went a little bit too far for my line. So let's do a recap on the problem. It's kind of cool. We have everything on one side, we have a 0 on the other side. Right now, my head's thinking, there's no way the intercept method's going to work because both of these are going to give me a y-intercept and an x-intercept of 0, 0, 0. That means I'm going through the origin. That also means I'm going through the origin. So we get the same thing twice. I know for certain I'm going through 0. My m is 4 over 1. My b is 0. There was no constant. There is no constant. There's still no constant. My b is 0. I have a y-intercept of 0, 0. From there, it'd be very difficult to graph this with the intercept method because you can't. If you solve for y carefully, negatives are a killer. Solve for y carefully, we get a slope of 4 over 1. Our rise is 4. Our run is 1. I already know I was going through the origin. That's where I start. That's where my first point is. Graph my line, show it goes forever. That's the reason why we need the slope-intercept method, is because it tells me explicitly and algebraically what my slope is without having to guess from a graph. Also, it makes things that the intercept method can't do possible for us. Walk through that example one more time, especially if you're bad with negatives. Those negatives can be a killer. So be careful on it. I hope that made sense. I hope that you can follow these down and get understanding about why we need that slope-intercept method. Next time we're going to talk about parallel lines and perpendicular lines. And another use for intercept method is because it gives a slope, we can talk about parallel and perpendicular now. I'll see you for that in the next video.